Well, good morning, everybody, and welcome. I want to thank you all for being here today, including those who are watching online. My name is Egill Viðarsson. I'm the CEO of Verkís. The discussion today is innovation in energy transition and new energy carriers. And in the fight against climate change, shifting the renewable energy is crucial. Transitioning to an energy system compatible with the carbon-constrained economy requires the extensive adoption of zero-carbon energy vectors. Even though there are sufficient renewable energy resources to meet the global energy demand, the geographical and temporal mismatch between resources and demand remains a challenge. Verkís seeks to identify solutions to utilize renewable energy sources while also considering current pressing challenges such as climate changes. We are constantly improving the implementation of sustainability in operation and projects and expect to see more advancements in the upcoming years, both within the company across the globe. We have a great program coming up. I want to thank you, our keynote speakers, for coming here today. I hope I will pronounce the name correctly. Kina Trauel and Christian Richter. Oh, he's not here. And Raun Merbekova. Albert Albertsson, our moderator today, is a mechanical engineer with master's degree in the Royal Technical University of Stockholm, Sweden. He is one of the front runners of the International Icelandic Deep Drilling Project. He outlined the resource park concept, harnessing natural resources in a sustainability and recycling way. As Albert himself has always said, waste does not exist, only valuable resources. He is now retired over 40 years of geothermal high temperature energy business. I will now give the floor to Albert. Thank you very much.
Thank you. Again, good morning, everybody. Today it is crystal clear that shifting to renewable energy is critical in the fight against climate change. This morning's seminar, Innovation in Energy Transition, New Energy Carriers, will discuss this matter in some detail. We are proud to receive two great professors to discuss this issue. Kina Trauel from McMaster University in Canada and Christian Richter from University of Iceland. Raun Merbekova, research scientist at Tæknisetur or IceTech, will also discuss the issue. First to the podium will be Kina Trauel. Kina is an assistant professor in the Department of Mechanical Engineering at McMaster University in Hamilton, Canada. She earned her PhD at McGill University, Montreal, Canada. Her research expertise is in high temperature, high pressure metal-water reactions for heat and hydrogen production. They also investigate the use of supercritical water as an oxidizer in metal water systems. In addition to her experimental work, Ms. Trauel researches the potential of metals as energy carriers and their role in decarbonized energy systems. She has several publications on these topics and holds a patent based on her research. Her research interests also include energy storage, energy for remote regions, the water energy nexus, and the techno-economic aspects of zero-carbon circular fuels. She is actively looking for collaborators in the areas of power generation, metallurgy, and metal production. Kina will talk about the concept of metal fuels and the basics of metal-water reactions for hydrogen production. Dear Kina, the podium is yours.
Hey, thank you for the great introduction, and I have to say it's my absolute pleasure to be here this morning. So as was mentioned, in the title of my talk is what I'm going to do. I'm not going to spend too much time on the idea of metal fuels because I think we have two other wonderful speakers who are going to go in more detail. But I do want to start this morning by talking about the motivation for doing this research. I don't think it's a surprise to anybody in this room that we need to transition to low carbon energy. Right now, and so when I say this to in some circles, the first question is, well, we don't have enough renewables. So I always just like to bat that out of the way. Right now, the global power demand is at about 17 terawatt. There's some research that indicates that with the efficiencies related to electrification, that can drop to around 12 terawatt or so. I say, while we're dreaming about this energy system of the future, why don't we make sure that everybody on Earth has enough energy accessible to them to just have a decent standard of living? Just enough energy to keep the traffic lights going and so that there's power at the hospital when you need surgery. If we look at it that way, we actually need about 40 terawatt. Okay, so much more than we even use today. And then we can compare that to what is available. So we have about 2 terawatt of water, another 40 to 80 of wind, 580 of sun. And you'll notice that I want to apologize on behalf of Jacobson and DeLucci for leaving out geothermal. I'm not sure why they did that. But this is based on technology. So this is actually accessible energy, not just the energy that hits the Earth, but this is accessible energy using technology from 2009. So clearly the challenge isn't one of supply. Really what it is it's related to the intermittency and variability of most renewable energy sources. This intermittency creates this storage and transportation problem, right? As I think somebody mentioned, there's this mismatch between when and where energy is needed and when and where it's available. In Canada, most of our energy demand is in the winter for heating, and most of the renewable power we get is in the summer. And so we have to start thinking about, okay, how do we capture and store that energy from the summer long enough to get us through the winter? And then in other regions, and Iceland may be one of them, there's a lot of energy here, but the only way we've been moving renewables around is through electrons, right? But building grids and connecting grids to where that energy needs to go isn't always feasible. So what we need is an energy carrier, something that liberates us from moving energy through the grid. So these energy vectors, again, if you've seen my SED talk, this is a little bit of a repeat, but I like to always just situate the audience. So this is every known element in the universe, and on Earth we typically get energy out of a substance through an oxidation reaction. So we need an element that reacts well with air or with water, and we have this transportation challenge, right? To make up for that geographical mismatch, and so we want things with high density. So anything with too high of a molecular weight will not be a suitable energy carrier. On the first slide, you started to get a sense of the scale. And so we need something that is abundant. We want to avoid these rare elements because not only would there not be enough, but they'd also be extremely expensive. Safety. So nothing that's toxic or becomes toxic once it's oxidized. And who here likes food? Okay. Well, I always take potassium off at this point because it's so important for agriculture. And so this is what's left. And it's not a surprise we see carbon up there. It's what forms the basis of our energy system now, and for good reason. What fossil fuels give us is something that is high energy density and high specific energy. And we can use combustion reactions to get that energy out. So that means we also have high power densities. And that gives us convenient things like airplanes. But greenhouse gas emissions, reduced air quality are some of the major drawbacks. And even if we weren't facing a climate challenge, fossil fuels are still a finite resource, and we can't just keep digging things out of the ground and burning them in this one direction. We need to start thinking about how to make our energy system reliant on something that's circular. So carbon is not it. And then there's hydrogen. Hydrogen is up there. And we hear a lot about the hydrogen economy. It's hydrogen's going to save us all. Hydrogen, hydrogen, hydrogen. Does that sound familiar? Right. And right, because hydrogen, you can burn it. It doesn't release, the oxide is water, which is nice. It has this high specific energy. But then it also has this extremely low energy density, which makes it very challenging to store and to transport. It's also a very small molecule, which also makes it hard to store and transport. Wide flammability range, 4 to 74%. So storing any great quantity of hydrogen is it's not something I want done near me. Anyway, so hydrogen itself may not be a great energy carrier. So some of the thoughts is, okay, well, we'll take those hydrogen molecules, we'll stabilize them with the nitrogen. Nature does this with carbon, but we can also make ammonia. And this is where ammonia lands on this figure. But ammonia has its own challenges. It's toxic and it's water soluble, which means that it can very easily get into natural waterways. And it's harmful to humans and the natural environment. So hydrogen, what I always say is that it's a great fuel, but it's a lousy energy carrier. And so what's left is this handful of metals, and we're already using metals as energy carriers. We use metals are the fuel in batteries, and this is where a lithium-ion battery falls on this figure. And they have low energy densities because they have to carry the fuel and the oxidizer and a whole package to go with that. Definitely part of the energy solution, and batteries are very convenient for carrying a bit of energy with you, your phone, laptop, even cars. But when we're talking about long duration energy storage and moving storage around, batteries just can't quite do it. But if we look at just the metal, so this is where lithium lands, and I just mapped out the rest of the metals that were left on the previous figure. And you'll see that most of these metals have these higher energy densities and specific energies. I put aluminum in purple because it's my favorite, and we're going to talk a lot more about aluminum today. Wait, do we say aluminum or aluminium?
Aluminium.
Aluminium, okay. I'll try and say aluminium. But it's written aluminum everywhere in this figure, or in this talk. So metals meet all of the criteria that we would want in an energy carrier. Energy density to store, very mature infrastructure. When it comes to common metals, we really know what we're doing. And metal fuels can be circular. So this is sort of how I like to envision a metal fuel system. So wherever it is that there's an abundance of clean energy, that's where the smelters are placed. In Quebec, where I did my graduate work, there's an abundance of hydroelectricity. So much that Quebec has somehow become the 4th largest producer of aluminum in the world, despite having 0 bauxite reserves. And it's all due to that cheap power. So we're already kind of doing this. Once that metal is made, it's effectively storing that clean energy and can do so for a long period of time without leaking that energy or degrading that energy. And then when the energy is needed, after either being shipped to wear or, months have passed and now the sun's not shining as much anymore and we need more energy. That's when the metal gets oxidized, fed to some kind of a prime mover. And then this is the key for the circle is to collect the oxides and then bring them back to wherever it is, there's that abundance of clean power to recycle them. In my research, I use water as the oxidizer rather than air. There's some really wonderful research going on in the direct combustion of metals. But in my research, I do these metal water reactions to produce heat and hydrogen. And, to produce heat and hydrogen. Now, this last bit, I just wanted to touch on it very quickly, is the scalability of metal fuels so that we can even narrow down the options a little bit more. If we do this very simple exercise where we say for some reason we needed to store 1 year's worth of energy in just one of these metals, this is how much of each metal we would need. And this is just a reflection of their specific energy. And then we can compare that to the known reserves of each of these metals. And with this very simple exercise, we can see that there's 3 metals here that are really contenders for a big scale, large scale energy storage, and that's iron, aluminum, and silicon. For metal water reactions of these 3 metals, aluminum is really the best one. It produces a lot of hydrogen. So it's about 1,200 milliliters per gram of aluminum. It's abundant, it's light, it's energy dense, and the technology for producing hydrogen is for producing aluminum is very mature. The one thing that still does need to be addressed when it comes to aluminum is the use of the carbon anodes in the smelters. They degrade as part of the smelting process and produce CO2, and this is a process emission. However, there's a lot of really exciting research in the use of inert anodes. And so these ones, they don't degrade, they last a lot longer. And so with the advent of these inert anodes, then this entire cycle using aluminum can be extremely low carbon or even 0 carbon. And in the interest of transparency, I do want to address, there's different ways that an aluminum water system could be deployed. And the first scenario is one where, so the reaction produces heat and hydrogen. So in a scenario where both the heat and hydrogen are used and the water doesn't need to be taken into account. So that means the water is readily available. So it's either a stationary application somewhere near a big body of water or a marine application where they're using both the heat and hydrogen, then this is where that system would lie in terms of its energy density and specific energy. In another scenario where the heat is ejected, but just the hydrogen is used and again, water is available, then the energy density falls where this 2 is here. The third scenario is one where water needs to be carried on board, but the heat and hydrogen are used. And so, think about maybe train, like some sort of like long distance terrestrial transportation. So like a train or trucking. So it would fall where that 3 is around ammonia. And then what I would consider the worst case scenario where just the hydrogen is used, the heat is ejected, and there's no water available, then the energy density falls to where that 4 is. And I also mapped the US Department of Energy's target for for hydrogen storage. And you can see that even with the worst case scenario, we're almost getting to that energy storage. So this is the general metal water reaction. And for aluminum, it follows one of 3 pathways. And this just depends on the temperature and pressure inside the reactor. And you can see in all cases, the amount of hydrogen is the same based on the amount of aluminum. The only thing that changes is the stoichiometric amount of water. And then those O's and H's just show up in the oxide. And then you also have, the same order of heat being produced in the reaction. So aluminum has, most of the applications with aluminum now are because aluminum is sort of like doesn't corrode. You'll hear that a lot, right? And that's because it has this very effective passivation layer. It's only a couple of nanometers thick, but it's very, very effective. And as a result, the reaction interface between the metal and the water is actually here, where the oxide meets the metal rather than at the surface. And as a result, the reaction proceeds in 3 phases. And the first one is what we call the induction phase. And in this phase, that oxide layer is weakened through the migration of OH ions. Eventually, it weakens enough that water can get through. And then we have what we call rapid oxidation. So this is where the heat and hydrogen are actually released. And then eventually, and then there's also at the same time, of course, it's oxidizing. So there's an oxide forming, and it becomes thicker and thicker and denser. Eventually, the reaction will quench. So it quenches for one of 2 reasons. One is all of the metal has been consumed, so the reaction stops, or the oxide layer or the new formed hydroxide layer is too thick or dense for water to migrate to the metal, and so what's left is this core of unreacted fuel. Most of the research in this field of metal water has been at low temperatures and enhancing the reaction at low temperatures. I just listed the most common approaches, and I'm not going to go into detail with any of them, but I'm happy to answer questions. I've left lots of time for questions. But they all have the same, they're all effective. These methods all work to enhance the reaction at low temperatures. But because there's this extra step, now there's increased complexity and expense. And then the other thing is that they have a low reaction onset temperature. Now, in these studies, that low reaction temperature is a feature. In my opinion, it's a bug, because it means that the reaction will happen at low temperatures. Not only is that a safety concern, but also half of the energy in the metal or an aluminum water reaction evolves as heat. So with a low temperature reaction, the heat that evolves is low quality heat, which is hard to use. And so that half of the energy of the fuel is going to be wasted with the low temperature reaction. So obviously in my research, I go the complete opposite way. These are experiments that were done by a predecessor of mine at McGill. And, just looking at the Arrhenius expression at the top, okay, we know that reaction rate increases exponentially with temperature. And this holds true for aluminum water reactions. And you can see that with a pretty modest increase in temperature, there's this, more than doubling in peak reaction rate. If you integrate these curves, that tells you the hydrogen yield. And so you can see also going up in temperature also increases not only the reaction rate, but also the efficiency or the hydrogen yield in each case. So when I started my research, I really had 3 big questions. Okay, so what happens if we go to even higher temperatures? How does this translate to other metals? And then how fast is all of this happening? So what happens at higher temperatures? Now, there was a lot of data for low temperature reactions. So just using that data, I just extrapolated these curves based on the size of the powder. So 12, 55, and 120 micron powder. These dashed lines indicated or sort of predicted what we thought we would see. And so you could see that, 12 micron powder, you would get the full hydrogen yield, but by the time you get to 120, it would be less than half. And this was based on what was out there in the theory at the time. So I did some experiments, very, very simple. Metal and water were loaded into a reactor, and it was sealed up. And then it would be heated to the temperature that we were interested in, held for a certain amount of time, and then cooled back down to room temperature. And the yield was calculated just comparing the initial and final pressure. So very, very simple, very straightforward. This is what the curves actually look like. And that's the actual apparatus there. It's not much to look at, I know, but what's happening inside is what we're interested in. So this, again, this is the prediction, and these were the results. So you can see that up until about 250 degrees, there's fairly good agreement with the prediction. And then there's this from 250 to the critical temperature of 373 degrees. There's much higher yield than what was expected. And then under supercritical conditions, we got full yield in the 55 and the 120 micron powder. And there's a 12 micron powder, we got full yield below that temperature. So 120 micron powder was sort of the biggest particle size that had been used. So, you know, as well as pushing temperature, I wanted to push size. So I used aluminum slugs, 2 millimeter aluminum plate, and then I started to investigate scrap metals. And again, fairly good agreement to 250 degrees. And I say fairly good agreement because the prediction was 0 for these size. You just can't see that dashed line. And then again, we see the transition zone and full yield in the supercritical temperatures. So I also like to show what the actual metals and products look like. So this is the metal slugs. They're about 3 millimeters in length and diameter. After 250 degrees, where there's very little hydrogen produced, and then 350 and at 380, which is the supercritical temperature I was using, what's left is this fine powder. With the soda can, the scrap metal, up to 350 degrees, there was no hydrogen production. And you can see that there's even like very superficial changes to the material itself. And then at 380 degrees, what's left is this fine powder. So clearly there's a couple of things happening here. The first one I'll talk about is what happens at around 250 degrees is that the ionic product of water peaks. So water can act as both a base and an acid. And all that means is that it can either give up or accept a hydrogen molecule. And the ionic product is just the product of the concentrations of H ions and OH ions in the fluid. And so as temperature increases, these forward reactions are favored, which means that the fluid becomes furnished with OH ions. What I didn't mention in these low temperature experiments where they were trying to catalyze the reaction, one of the most common ways of catalyzing the reaction is the addition of a base like sodium hydroxide or potassium hydroxide. So by adding that base, there's more OH ions, and that's what attacks the passivation layer. But by going up in temperature and pressure alone, we get that. I don't want to say catalytic effect because it's not a catalyst. It's really just the change in the water properties themselves. So you can see here that it peaks, and it's this change in water property that really enhances the reaction and why we get that much higher yields in that transition zone. And then this was also quite remarkable, you know, going from something that really resembles metal to a powder. And this is due to the change in polarity of supercritical water. So under relative permittivity is what governs solubility, and under supercritical normal temperature or normal conditions for water, water's quite polar and dissolves polar species like salt. But at the critical point, it drops to sort of 1 to 10. And this is because of, that range is just a function of pressure. And so it becomes almost completely nonpolar, which means that it can start to dissolve nonpolar species. And the nonpolar species that we're really interested in dissolving here would be the hydroxide that forms in the reaction. And so my hypothesis is that the formed hydroxides are either dissolving or they're just not cohesive enough to passivate the metal. So the metal is continuously exposed to the oxidizer until it's completely consumed. And the form of the oxides kind of supports this hypothesis. So that's the first question. Going up in temperature helps the reaction. Great. How does this translate to other metals? For these experiments, I did take out most of the group 1 and group 2 metals because we know how reactive they are with water, which is very. And so just in the interest of safety, we didn't do experiments with them. I also removed boron and iron because I can go into detail of why, but they're not expected to be very reactive with water. And then I brought back titanium and zirconium because there were some low temperature experiments that were done that showed that these were promising in terms of their reactivity with water. And this is what I found. So this is what was expected in every case, just based on a simple calculation. And this is what was found. So you can see that with the aluminum, it's alloys, magnesium, and zinc. Under supercritical conditions, we get full yield, or in almost all the cases, but very, very good even with the aluminum 6061. Whereas the silicon and zirconium, I mean, I would say underperformed, but what this is just telling us is that these are potentially great materials for designing or for using in the system. And titanium as well, there was zero hydrogen produced. There were changes to the metal, like you could see them. You could see them also under SEM, but there was no hydrogen produced. And then finally, how fast does this reaction occur? So what I was really interested in is this region of the vapor dome. That star is the critical point, and so this is the isotherm that I was following. And so I was interested in the role of density, of the water density. And so for these experiments, I built a new apparatus. It had a top and a bottom reactor separated by a valve. And in the experiments, everything was loaded and then heated up to the temperature. When we were at the temperature, the valve was opened. They mixed, produced hydrogen, and then everything would be cooled back down. So like I said, I used sort of 3 densities of water, what I'll call the high density supercritical water, the low density supercritical water, and then the vapor density water. And so this is the hydrogen evolution for the high density water. So you can see that that 10 micron powder performed very well. These were the results for the rest of the experiments. And so you can see that there's not much of a difference in terms of the yield for the high density and low density supercritical water, but there's a big drop off for the vapor density water. That wasn't such a surprise. And then with the rates, it was a different story. So here, there's a big difference between the high density and low density supercritical water, but not much of a difference between the low density and the vapor density water. And this held for all of the samples. So those are the results for the 10 micron powder. But you can see all of them. So there's a big difference between sort of this and this, but not so much between this and this. This was a little bit counterintuitive. It wasn't what I was expecting to see, because the low density supercritical water has the properties that seem to be desirable for oxidation, right? Low viscosity, high diffusion rate, high relative permittivity. These are all the things that indicate it would be a good oxidizer. But we saw the opposite. And so what that tells us is that there's some relationship between the reaction rate and density or pressure. And so, if we're writing an Arrhenius expression for this reaction, we would need to somehow capture the concentration of OH ions, is my current thinking. So, we've identified 3 metals that are promising as metal fuels. And we've also determined that increased water density or pressure is conducive to higher reaction rates. And so what comes next is what I want to share with you. So one of the things I'm really interested in is the effect of water quality. Everything I've shown today has really been based on, all of those experiments were done with very, very pure water. Science, so we use reverse osmosis water, but in the real world, that's not what we'll use. So I'm interested in, okay, if there's salt for marine applications, or if there's organic material in the water, how does that affect the quality of the hydrogen that's produced? And, does it poison the reaction, enhance the reaction? These are all sort of open questions. I'm also really interested in how we can optimize the oxides for recycling. We know that based on how the conditions inside the reactor, we can tune certain things about the solid product that is produced. So we can make the particles larger, smaller, we can do some things with the grain sizes. So that's something that's really interesting that I'd like to start to work on. And then finally, okay, great, we can produce heat and hydrogen. Now, how do we start to use it? And so that's another area of research that I'm looking to branch into. So I want to stop here, and I think there's time for questions. I hope I left time for questions.
Of course.
Yes.
You're quite focused on the yield of hydrogen. While in Canada, it's actually heat which you need in the wintertime.
Mhm.
So as an energy carrier, heat is the most important. So why are you so focused on the yield of hydrogen?
So that's a great question, and it's not so much that I'm focused on hydrogen. It's that I've been using hydrogen, and I probably should have said this, as a placeholder for heat and hydrogen. So with aluminum water reactions, half of the energy evolves as heat and the other half as energy, and that's just how the reaction runs. So you can't tune it to get more heat or more hydrogen. So if we have an efficient reaction that produces all of the hydrogen, then that reaction also produced all of the heat that could have been produced. Does that answer your question?
Yeah. Can I have another one? Also, you had quite small particles there, down to 10 microparticles. In an industrial scale, would that cause explosion risk?
10 micron. It doesn't have an explosion risk the way that some of the nano powders do. But metal powders under the size of 50 micron are now export controlled in a lot of countries. So that's also one of the reasons that, practically speaking, I'm interested in these larger particles. So going up to, the size of, on the millimeter scale. Those would be the cheapest to produce, the easiest to produce, wouldn't run into export issues or import issues. But just in terms of understanding the fundamentals of the system, I did want to use the finer powders and get that range. So going from 10 micron, like the micron, to the millimeter size.
So it's around 420 micrometers for the safety. It has to be larger than 420 micrometers.
For aluminum.
Mm-hmm.
Oh, really?
Mm-hmm.
Well, it depends.
Yes.
Yeah, you said there is low temperature oxidation. Have you considered any storage methods for these powders so that they don't lose their energy over time, for example, in nitrogen tanks or something like that?
So with I don't really keep any nano powders on hand. I've used like some of the 1 and 10 micron powders that I used in earlier experiments. We just kept them in plastic containers with a lid, and they were still reactive. And there was no difference between new powders and the old powders, because that passivation layer on aluminum is very, very effective. Once we get into finer, so like sub-micron size powders, those ones we do store under, in our lab, it was argon that we would store them under in order to prevent them from premature oxidation. But again, that's also in the interest of why we want to go to the larger particles, is because with very, very fine particles, sort of on the nanoscale, if you think about that passivation layer, it's always 2 to 3 nanometers thick. So the proportion of metal to oxide is much larger when it's a fine and much smaller when it's a large one. So that's why my focus is really shifted to these coarser particles.
How is this powder produced? Is it produced on site, or is it moved? You need to produce the powder on site where the reactor is.
Again, when I think about this system, I would think that it would probably be easiest and best to produce it where the metal itself is produced. So rather than shipping ingots and then trying to figure out how to turn those into a powder on site, just simply producing the metal fuel in the form that it would be fed into the reactor. To me, that like instinctively that makes sense, but I'm just basing that on what.
Can you test the oxidation layer by producing the powder on site?
Oh, okay, now I understand the question. If you wanted to just completely avoid having that passivation layer, you could produce the powder. You have to produce the powder under an inert environment and keep it in an inert environment until it's fed into the reactor. So logistically, I just think that would be challenging and not entirely necessary if you go up to high enough temperatures and pressures.
Have you studied the quality of the hydrogen?
No.
Ah, okay.
Great question, though. What I can tell you about the hydrogen that's produced is that it's not. You couldn't just feed it straight into a PEM cell because there would be water vapor coming with it. So then the question becomes, okay, how do we separating out the solids from the gas is easy, and then okay, how do we separate the water from the hydrogen? That's next steps. Yeah, that's a great question.
Talking about the water, how water intensive is the process?
Depending on the reaction pathway, it's 1-to-1 by mass to 1.3 to 1 by mass. So the most efficient at 1-to-1 by mass is the reaction pathway that produces alumina directly, which is the goal. With these experiments, it was the second pathway. So the product was AlOOH. So there's a little bit of an extra O and a extra H. And so that was the water intensity there is about 1.1 something to 1 by mass.
It's more or less similar for pure water and brackish water.
Yes, yeah. We only did a handful of experiments using that saline water, but there's no difference really. I just saw somebody online, Karen.
Yeah, thank you, Kina, for the introduction and the presentation. I jumped in the middle, so maybe I missed the introduction in the beginning, but for 1 unit of energy that you get in the process, how much do you get out of a process? Are there any losses?
Oh, yes. So I'm going to just do a very quick and dirty cycle, energy efficiency cycle. So for every unit of clean energy that goes into the smelters are typically about 60% efficient. So we have that. So there's the 40% loss, and now we have, let's say, 0.6 of a unit of energy coming through. This reaction, if we get the full heat and hydrogen yield, then there's no loss at this step. So we have 0.6 of an energy unit coming out here. And then depending on what the prime mover is, we'll have another loss. So if it's if that heat is not used or not stored, then we've lost half. So we have 0.3 of a unit. If we're able to use both of them, then we still have that 0.6. But the best case scenario would be some sort of a system that combined a steam turbine with a fuel cell. And in that case, we would get about 40% efficiency. So that would mean we'd have 0.25 of a unit sort of to use. So that sounds terrible, I know. But thermodynamics are a reality. But when we compare that to, say, using an electrolyzer and producing hydrogen, and then either making ammonia with that and then cracking that ammonia, that 1 unit of energy comes to about 0.13 units. If we make hydrogen and then liquefy that hydrogen and then use that hydrogen in, let's say, a PEM cell, then we would get at about 0.22 of a unit. So those are the kind of numbers we're talking about when we run these multiple processes. Does that answer your question, Karin?
Yeah, thank you. Very instructive.
Yeah, so I wonder, now the aluminum smelters that we work with are highly dependent on baseload energy. They're not so flexible, to my knowledge, to use intermittent energy. Do you know if there's research going into that?
That's where I need to sort of find the right collaborator to start to look at that question. It's the same reason that, like, in Quebec, because it's hydropower, there's that big baseload of energy, right? So it's a really good question that I don't have an answer to. But you're right, like aluminum smelters can't load follow directly to something like wind or solar necessarily, right? But can they load follow if you have a good base load, and then you can use the smelters to sort of balance the rest of the grid? So that, like, I know that there's people who are looking at doing that, and in Hamilton, where I live, there's a little bit of that happening, where Hamilton historically has been a very industrial city. And there's been some factories and some processors there who will sort of ramp up and down their production to help balance the grid. So, can that be done with aluminum smelters? I don't know, but I would be very interested in finding out. Great question, thank you.
You said that there are several methods removing the oxide layer, and I'm curious which one is your favorite?
None. None, because like aluminum, that oxide layer forms the instant it's exposed to oxygen, right? So if you're getting into the business of removing that oxide layer, then it has to be done and kept under inert conditions. So part of going up to the higher temperatures and pressures is to remove the need to remove that oxide layer or do anything with that oxide layer. And the low temperature reactions, one of the more interesting one, I think, and this is the basis of that of found energy, is using gallium to disrupt the oxide layer. And I think that one's really interesting because the gallium doesn't participate in the reaction, and so you don't need to be continuously feeding gallium into your system. You can sort of just recirculate that gallium, and you don't have, and it doesn't, because it doesn't participate in the reaction, it doesn't negatively impact the oxides that are left over at the end. So if I have to remove it, I think that's the most interesting approach to me.
How does the impurities in the aluminum affect the process?
Yeah, that's a great question. So from what I saw with the two alloys that I use, the 6061 and 5052, the alloying elements of the 6061, which was the one that didn't react completely even under supercritical conditions, the alloying elements were, there were more alloying elements in that one that are known to be poorly reactive. So there's a higher silicon and copper content in 6061 than in 5052. So again, it was just a one set of experiments. And I think what's happening there is that's what's not poisoning the reaction, but slowing it. But more work needs to be done to really understand the fundamental mechanism there.
Magnesium, what effect does that?
Yeah, it increases reactivity because it's very, very reactive. Not as reactive as calcium or lithium with water, but it's up there. Yes.
Have you studied the byproducts, aluminum hydroxide and aluminum?
Yeah, so once we were sort of above 250 degrees, the product was no, it wasn't alumina. It was AlOOH.
Oh,
So I think we call that baemite. But I'm looking at trying to tune the reaction so we get alumina out at the other end, because I do believe hydrogen is a no-go element for smelters. Yeah, so there would have to be some sort of calcination of the alumina afterwards, yeah. Okay.
My last question.
Mhm.
When can we see the demonstration unit of 1 megawatt? What is
I'm working on the grant application. Yeah. Yeah, I think that, maybe I'm biased because this is the research that I do, but I'm really looking forward to seeing something like this in the real world, because I think it will fit. It'll really solve, some of the more challenging parts of decarbonization. There are certain sectors that we just don't have a good solution yet. Long distance transportation, marine transportation, and I really think something like this would fit that bill very nicely.
Very interesting. Okay. More questions?
I think I'm actually over time by the schedule that I was sent. So.
Okay, next to the floor is Christian Petrus. Is he here?
Yes.
Okay, there you are.
Nice if he wasn't.
Christian Petrus is a professor of chemical engineering at the University of Iceland. He will introduce the work of the ALICE, do you say Y project?
That's right.
A project on the hydrolysis of waste aluminum, and say a few words about hydrogen and e-fuel in Iceland. Please, the floor is yours.
Will help me to get the talk. Thank you. So while she gets the talk up, I will just start by saying, so it turns out that there are 2 projects in this field that Kina gave us a presentation on, where Icelanders are participating. And I will sort of briefly, in my 10 minutes, just introduce one of the projects, and then Ruan will introduce the other one. But before I think, I would just say, as somebody who has now been working a little bit in this area, I think, in my opinion, this is as expert a presentation in this area as we could have gotten. And so having worked now on our project for 3 years, I sort of came to the same conclusion. You will see that the projects that I will be talking about is working on the lower temperature end, but I also came to the conclusion that probably if we want to use this for energy storage, we have to do all the things that Kina's been talking about. Go to a high temperature, especially if you want to harvest the maximum heat, etc. So that's sort of my brief introduction on that. And then I just want to introduce myself, because it's my first time here at Verkís. I've been in Iceland since 2016, in part so that we could have a complete BS degree in chemical engineering. I'm sure even at Verkís you've got chemical engineers that somehow managed to get a BS degree in, and of course they didn't take it. Or we in Iceland had a complete BS program, but that's why I was important in 2016. And then the main thing that I keep myself busy with since 2019 is sort of exploring the possibility we have in Iceland to produce e-fuels, with the hydrogen, methanol, where we kind of are a world leader in some or other way, ammonia, methane. And I've been very busy with that. And I sort of just wanted to advertise and reach out to the Verkís engineers. There have many projects that come and gone, but some of us have already visited EPLA, just because, as you may have noticed, about 6 months ago, EPLA did do a website with Lunchvik, and they were maybe the consultant, maybe Lunchvik can pay them. But at this point, of course, and this relates to today's talk, we in Iceland may also participate in this type of reality, this type of opportunity in the world, that is to produce energy and to move it, right? For example, we can produce energy and make a fuel and make that part of our fuel mix for our fishing fleet, for our diesel trucks. Or we could also move energy, and as you'll see in Ruan's project, she's working with Swiss people, and they're imagining maybe moving energy from Iceland in the way we've just seen. So we could choose in Iceland to participate in this or not. Maybe it's a good idea, maybe not. But the thing that will determine whether or not this will happen, of course, as you all know, is will we have the energy? And we will only have the energy if we let in a little, decide as Icelanders it's worthwhile to have a little bit more, which means, of course, the dams, like Verkís, that has been stuck for a decade, or maybe another dam. We need to decide it's worth it, worth the environmental impact, and also letting in wind. So this is sort of advocacy in Iceland, and this is why, sort of the EPO people have already visited Epla, because they have sort of just landed on the roof, and there's a website called, orkaskipti.is. But I am very aware that Verkís have maybe as much to contribute. And when I say for advocacy, it's really two things, right? It is the Icelandic people, but specifically those decision makers on the master plan committees, etc., who will decide whether or not we should have wind. And then finally, of course, in Landsvirkjun has a lot of power to decide, even if we do get extra energy, who gets it. Okay, sorry, this is just a pitch who I am and what I'm actually working on mainly, and sort of the, stuff like hydrogen and methanol. And then I'm also involved in the project. I'm going to now spend the next 5 minutes to just introduce, so you can have an idea of what is some Icelanders working on in the same field that Kina has spoken about. And so the project, the name is there. I didn't come up with it, so I'm glad everyone to answer the question about how to pronounce it. But of course, here's the partners in our project. It's Lithuanian, Latvian, Icelandic collaboration. There is the Baltic institutions, and then you'll see Taiki Center or ISTEC, used to be Innovation Center, is involved in both projects. And so everyone will talk about the second one. And in this particular project, we at the University of Iceland is also a partner. And this has been very well presented in Kina's presentation. But basic idea is that you can have aluminum reacting with water quite vigorously if you get past the passivation layer. And you can do that with some of these tricks that she presented on, or by just going up in temperature. And I think if you're going to do a big commercial installation, maybe going up in temperature is the simplest. The most common approach, if you look at the literature, is also the one that's being used in the project that we have partnered with. Oh, of course, you can hear. So this is the project that the Lithuanian Latvians, we are doing the most common approach, which she has briefly mentioned, where you throw in a strong base, sodium hydroxide or potassium hydroxide, to get the reaction going. And then the temperature can be as low as 20 Celsius. It typically heats itself up to 80 Celsius if you don't cool it. Okay, and then in our particular project, the one we're doing with Lithuanian Latvians, we are basically just focusing on waste aluminum, so scrap. And it turns out, if you research it a little bit, we are doing pretty well with cans. So as long as people deposit the can, you can remelt the can, and it's probably the best thing you should do with it. So this is probably not the best material to react, because it's just better to remelt it. And then we have been looking into dross a little bit. We even got samples from Alcoa and Fjarðarál to look into it. But the main opportunity that we have seen so far is in some of the scrap metal. If you really look deeply, I'll give you the short answer. If you can remelt it, it's the best thing, just to remelt it. But sometimes there is not a match for the alloy. And then rather than, oops, should I just hang up? Or you can hang up from there. Yes, so this is primarily the background of this project. Take scrap metals that you cannot just remelt, and then see if you can extract value out of it by harvesting some hydrogen and producing aluminum hydroxide first, which you can calcine, and then you have basically alumina that you can return to the smelters. So it's basically a recycling option. Okay. So yeah, let's say these things, basically saying where the opportunities is in recycling. So it's basically what Kina talked about, but now with the focus is on optimal recycling, getting maximum value out from a waste that you cannot remelt. So in our project, there's many aspects. Our Lithuanian, Latvian counterparts they've got a lot of equipment, and they also play with plasmas and nuclear physics, the sort of old Soviet remnants. So they're not afraid to do experiments in all kinds of conditions. So both of these institutes independently, they both are making reactor prototypes. So this is their role. So if you want to see a prototype reactor, you can go visit them. Then they also modeled together with helped a little bit the reactions. Something people do. And then we published 2 papers, and I'm going to talk about this one. That's why I've circled it, just because it appeared today. So it's like a fresh result. I don't know, you Icelanders, we of course love brave Coke for the fresh baking goods and bread and snooders and whatever. It comes fresh from the oven. So the only reason I'm really going to pick this one result to share among the many is just because it's fresh. It came out today. The relevant article, you could see it today for the first time. Okay. And then finally, Tidy said that is very much involved by characterizing, for example, the dross from the smelters, seeing what's in there, and then also the solid products. And then our final job and project is to do techno-economic analysis. Okay, and then I'm going to now jump to this fresh result and I'll give you the main overview. And I know it's a bit messy slides because it's the first time I've been sharing it with anybody, like the article just came out. But essentially what is on the board here is just the idea. I mean, you can the main idea of the project. But to understand the little result I will share now here is in the simplest understanding of what is the chemistry, certainly the lower temperature, because the product slightly changes when you go up in temperature, as you heard earlier. But what is the chemistry that's happening? So the first chemistry that is happening is that the aluminum can dissolve. And again, this might change, by the way, in high temperatures. So, but if you have a very basic solution like what we do, pH 14 or 13, then the aluminum metal can completely dissolve. In fact, our Swiss colleagues have done beautiful experiments where they just show you, you can see you throw in the powder, and if you don't have too much powder, so it's saturated, it's all gone. The aluminum can, at the low temperature with a high basic pH, this is the first step. The aluminum dissolves. Then there's another step, which is, of course, when the aluminum atom leaves as an ion, it leaves behind electrons in the solid aluminum particle. And that then can evolve the hydrogen, basically split water. And then finally, I admit now what I'm telling you is one idea of what happens, of course. And we're going to see what I'm going to show you now is that in this result that we've just published, we're sort of checking how much does the data correspond to this model. And I think as the temperature goes up, the mechanism might slightly change, or the path of how the hydrogen comes out in the aluminum react. And then finally, this aluminum ions can at some point, if there's enough of them, they deposit and make new aluminum hydroxide particles. So this is basically one way we could say, if we want to look at the chemistry of this, the most commonly cited in the literature, most commonly believed for the low temperature version of this, how do we get hydrogen? How do we turn aluminum metal and aluminum hydroxide? This is the 3 steps. And then the key thing I will just show over here. So, okay, there you see sort of something more similar to what might be happening at a high temperature, that we have a core shell reaction, where actually the aluminum doesn't dissolve, it's just the reaction heats up the particle towards the middle, and then the unreacted part in the middle may stay unreacted, and you don't have maximum yield. The nice thing is, but you have to use a high base concentration at a low temperature, but we get almost always 100% yield. And it's not a surprise, if we do it so that all the aluminum dissolve. Okay, so now we'll get to the point so that you can sort of understand just the result, and that's all I will do today. And that is, if you look at each of these steps, first time I did it, I thought okay, this is sort of just cartoons to show the steps, but I actually don't want to spend too much time on come to the main result. Just sort of describing the pictures for these steps. This is what I want to show. So the very first step, if you carefully look at the reaction, you will see that it consumes 4 hydroxyl ions. So if the first step alone were to happen, and the other 2 steps did not yet happen, what you will see is your OH minus, your hydroxyl ions, will get less. And that corresponds, if you guys think back to high school, if you haven't done it recently, or if you work with electrochemistry a lot, if you reduce your OH minus ions, means your pH goes down. So this is the main thing that we have published now. We realized if we look at the pH in the reactor, we should be able to see if, for example, this happens first, and then this, or does it all happen simultaneously? For example, there should be a pH change as this step happens. And then if you look at the next step, you can see now where the game is. When the water splits, it actually produces 3 hydroxyls. Because that's where the hydrogen comes from. It takes one hydrogen atom to make the hydrogen, and the other OH minus stays behind. So the next step would put back 3 hydroxyls. So for example, if this alone happens first and the other two don't happen, the pH will go down a lot. If these two things happen, for example, simultaneously, then the pH will go down just a little bit. And then finally, you will see if things happen perfectly the way it's written down, the final step gives us back one hydroxyl ion. So then we consumed 4, we got 4 back. And so the whole net thing will have no pH change. Except, of course, if there's side reactions or we're wrong about what we think is the reaction. Okay, so now I'll just show you the data. There's 2 slides and then I'm done because I only have 10 minutes. What I'm just showing you here now is, maybe I should start here. So what our colleagues, this was all done in Lithuania, these experiments that I share with you now. The blue here shows you the hydrogen yield. So you could see through all of these time and seconds, hydrogen is being made all the time. So the reaction is going. And then what you see over here on the side, this is the same time scale, is this data is just we are tracking the pH. But it's not as if even at the end, the hydrogen is still being made. And you'll see in the next slide, at different conditions, the pH stopped changing, but the hydrogen is still coming. So we probably have all 3 of those reactions happening in balance. But as you can see here, and I'm going to show you just 2 results with that many different. This is at the least basic solution we have studied. Then we get this phenomenon, which is more or less what we expected, that pH goes down slightly and then stabilizes. Meaning some of the early reactions that consume more OH minus, maybe it's happening a little faster than the rest. And then in the end, the other reactions catches up. And then sort of what I've just drawn here with the dashed line is if you then take how much hydrogen is being made, and then you assume various cases of, just the first reaction outcome, first and the second, you can sort of track how the pH should have changed. And you can see basically that the data is not perfect match, but it pretty well match the scenario where the pH is going down only with one OH minus per aluminum atom. So it's basically the scenario where this happens and this happens. Both of these reactions happen, but the precipitation does not yet happen. That's what fits the data at this moderate basic pH. So, and then of course, if you wait long enough, then and you let this go long enough, then the aluminum hydroxide starts precipitating and the pH completely goes flat. So at this not terribly basic conditions, it seems to fit the basic model well. But now we go just double the basicity. We add twice as much base, and the behavior got a little bit more weird. Instead of the pH going down, it went up. So the only way in our basic model to explain it would be, which we did not expect, it would mean that this happens first before that. So it appears the aluminum is not dissolving as we assume, more something like this in hydrogen. And then at some point it goes completely flat, which means then all 3 of the reactions appear to be happening. So this is all I'm going to share. Just the basic take-home idea, which we can sort of take right up here in Iceland, is this idea of measuring the pH to see what's going on. We and the Lithuanian Latvians came up with it. Maybe some other people have done it. Have you done it? No. So, of course, other people may have done it, but we couldn't find it in the literature. So I thought it's something to share. And also just because it's a fresh result. And it relates a little bit about how things are going. That is it for me. Okay, yeah. So right there. This is sort of the conclusions. What I just shared. That's it.
Some question for Christian?
You can ask some of the previous questions again. They were also good. And we also have a take on all of them. I'll take the one about the intermittent aluminum smelters, because that's something we in the e-fuel community is also very involved. So when it comes to producing e-fuel electrolysis, that is, of course, in principle, very flexible. So one of the things that's been happening in the last 6 months, one of the e-fuel projects, Carbon Iceland, has been meeting with all 3 of the smelters, because we can really have an alliance, firstly, because the smelters have the CO2, because of these anodes that are burning, so that we can package our hydrogen and methanol. And then secondly, we're actually partners when it comes to energy. Both the smelters and e-fuel, we will do better in Iceland if we are not so starved for energy. We are in Iceland. We have not had a new dam for 10 years. And my home country, South Africa, we have done the same thing, and now there's rolling blackouts. So generally speaking, at some point, as the country grows, we need more energy. So that's one way we could do it. The e-fuel project and smelters can work next to each other, and the projects can be designed from the ground up, right? And that's really why we're reaching out to EPI and Verkís, and we would have many subcontracts, of course, if these things were to realize nice, to be flexible, and then we would actually be a partner with the smelters, help them levelize out. The other possibility, and this is the last thing I know, this is the last thing I'll say. You were there to NASCOPE in Iceland, that seminar we had at the hospital in Reykjavik about 4 or 5 months ago.
No, I don't think so.
You weren't there? Anyway, there were some German smelters, which is similar to what Kina, and they,
Oh, yeah, 3 months.
yes, yeah, 3 minutes. So if you want to dig into that, so I think conventionally the thinking is certainly we talk about Icelandic smelters. Okay, I'll just talk over them. So our Icelandic smelters is that we're not flexible, and certainly that's how we set up in Iceland. But these guys have the stream it, and guys, what happened. What happened in Europe, of course, in Germany, is because of the Ukraine war, the energy prices spiked incredibly, so they become completely unprofitable to operate. But as you also know, smelters don't want to, and they have really managed to become sort of intermittent, and the details on how they did it and etc. that may even have been recorded. So they were the main speakers this year's Aluminum Society.
Alklassen.
Yeah, Alklassen. They were the main speakers, and you could probably see his talk and see how they've done it. So that is possible. I think it's still harder for the smelters to be flexible than it is for certain kinds of electrolysis plants, but it's not undoable. Okay, then I'll give you the floor.
Okay, the last on the floor is Alan Merbekova. Dr. Alan has over 12 years of experience in academia and industrial working with metal production. Currently, she works as a senior research scientist at Tecnised or ISTEC on various green technologies, where they develop CO2-free metal production. He will talk about the Reveal project, a new technical solution for storing large amount of energy at low cost for producing heat and electricity using aluminum as a renewable fuel. The floor is yours, please.
Yeah, thank you. It's actually a great honor speaking here. It was Verkís has been my first workplace, and I had a very good impressions, and my colleagues were very friendly and nice, which helped me to come up with Iceland. So I'm presenting this review project. This project is co-funded with the European Union Horizon program and Swiss State Secretariat for Education, Research and Innovation. The idea came from our Swiss partners, where energy demand was more during wintertime, especially for heating. So this project develops a solution for storing large amount of energy with very high storage energy density, more than 15 megawatt-hour per cubic meter, at low cost for producing heat and electricity. So we started this project last year. The main goals are seasonal energy storage cycle, power to aluminum, which is our storage charging, aluminum to energy, which is our storage discharging, and life cycle and economic analysis. So the concept is storing renewable energy over longer time at an attractive cost, and as I said, an acceptable environmental impact. So the situation is that we have now cheap renewable energy, and we have also the solutions for the short-term storage, but we don't have solutions for the seasonal storage for the longer time spans. So for that, we came up with a solution which we will convert aluminum oxide into aluminum electrochemically. And because in this process, electricity involved, our aluminum becomes a renewable fuel. And as I said, it has a very high energy density as it stores a lot of energy inside, which is about 23 megawatt hour per cubic meter, which is 8 kilowatt hour per kilo. And we can actually use it and produce energy. And it's actually easily also transportable. As you can see, it's a solid product and it doesn't degrade for months or even decades. And actually in Iceland, the main thing is that I think this project will drive the need for the low carbon aluminium. And in Iceland, we are developing a technology without producing aluminium without CO2 emissions. So this is a project with Arctus and Tech Center. We have recently gained our partners from the Fremont who are supporting us and we're doing the pilot scale. So I can circulate this around so you can take a look at it. So the thing is, you take this aluminium and you have the water and you produce the hydrogen, and the byproduct is aluminum hydroxide, which can be after heating back converted to the aluminum oxide, which we can feed back to the smelter. So this is a closed life cycle. And we study here like two processes with both low temperature and high temperature. We have 9 partners from 7 European countries: Iceland, Slovenia, Norway, Netherlands, Czech Republic, Germany, and Switzerland. Tech is a main coordinator of the project here, and we also work on the power to aluminium, which is green aluminium production. And this is our social media. You can follow us in the social media. And thank you. Which is very great, actually, like I said, we are very small in Iceland, but we are like developing and competing with large giants. For instance, this CO2-free aluminium production, we are competing with Alesis, which is supported by Rio Tinto, Alcoa, and Apple. And another competitor is in Russia, it's Rusal, it's also another giant. And in Iceland, we have been developing this more than like 10 years, and just recently, Fremont started supporting us, and we're doing a pilot scale there. So it's very remarkable, I think.
To jump in here on the first, so this aluminum that you're sending around, this is what you and Arctus have made
Yes.
part of the reactor.
Yes.
So CO2-free aluminum.
Yes, exactly.
Yes. Very special.
Mhm.
Wasn't the CO2-free production of aluminum being developed in Russia a few years ago?
Yes, exactly. That's why I'm saying we're competing with them. So actually, I think this technology will actually help us to kind of transport the renewable energy from Iceland to other countries where maybe renewable energy is not an option. For instance, in Asia or some other like remote countries. Yeah. Mhm.
You should put, so we can be extra proud, put it on your Reykjavik, Iceland, or whatever. It's your neighborhood.
Yeah, exactly.
Outby or whatever, wherever you guys are. So that people will know, plant the flag.
It's so actually like Rusal and the Alesis, they have we believe we have similar process by Rusal, but everything is confidential. Of course, we don't know. But the Alesis is slightly different. They use as an inner process. So how do we get the process CO2-free? Is that usually in aluminum you use carbon anodes inside the process. That's why you produce CO2 emissions. What we are trying to do is like replace these carbon anodes with inert anodes, which is supposed to not like react with the not be consumed. So you instead produce just oxygen in the reaction.
So with the inert anodes, does that change the amount of power needed or the amount of energy needed to produce the aluminum?
It's actually, it changes actually because carbon is like extra energy source. source, but we'll not have it. But the thing is with inert anodes, what we're thinking is that you can have like more isolation because currently, like as you mentioned, overall process, conventional, it's like up to 60% efficient. So it's a lot of energy losses because you have this graphite is very corrosive and you have to have the cell design. So you have to have these losses, heat losses. But this new technology is very different. So we're thinking of having kind of isolation. But therefore, we like think it will be like a lower actually energy demand because of that.
Okay.
Because this is really different. Because, for instance, here we have vertical electrodes, and we can place them very close to each other. For instance, in aluminum smelters, it's different. It's a very big carbon anode, and then your cathode is aluminum below, and you have to have like a very big distance between. It's like about 3-4 centimeters. But with vertical electrodes, we can place them very close to each other, which also eliminates the energy losses. Yeah.
Yeah, related question. So in the end, everything boils down to cost, right? And we were kind of referring to that. And another option would be like for the aluminum smelters, just to capture the carbon, store it, or mineralize it, for example. Do you have any thoughts on, is this cheaper? If you save energy, is it going to be cheaper or?
We believe this is cheaper because the thing is with the carbon capture, you have to have concentrated CO2 to be able to capture and store it. And currently in aluminum industry, it's not possible. You have to make this change in infrastructure in order to concentrate the CO2 you are getting there. So this is also very expensive. But with this, for instance, this technology with the aluminum, you have it everywhere. Okay, this is here we are maybe producing aluminum, but which maybe will be costly. But also we have in Iceland low carbon aluminum. And or like a lot of Aliswai actually project, it actually rotates with recycling aluminum. For instance, actually not many people think aluminum is like indefinitely recycled and everything is recycled, but actually it's very hard to recycle aluminum. It's very hard to if you don't know what is inside the aluminum. So you actually have to know what is inside the aluminum to be able to recycle. So for instance, that's why the cans and everything is easily recyclable, but other materials it's hard to recycle. We don't know what is inside it. So that's why, for instance, you can take one of the recycle option is like producing the hydrogen from this aluminum scrap. So I think that's another great project, and it's everywhere is aluminum scrap. Instead of landfilling it, you can actually have another life for it, and it contains a lot of energy inside it, which is why we waste it. So, and as the Kina mentioned, this aluminum water reaction is very mature and well known, and it's not so expensive, isn't it, Kina? Yeah.
Depends on who you ask. If you ask me, I think it is a very reasonable price in terms of cents per kilowatt hour out. But there's always people who say, oh, aluminum is expensive.
Yeah.
Oh, it takes a lot of energy. Well, yes, it stores a lot of energy.
Yeah. In our actually project of Swiss partners, they calculate that it's gonna be less than. May I say yeah? I think yeah. I can say that. It's gonna be less than 7 cents per kilowatt hour, which is very cheap, and that's why it's going to be very affordable, and it's going to be affordable not only for just industry, but also the plan is to have it like domestic. So everyone at home, you can actually have this reactor with you at home, and where you can actually you have a storage facility for yourself. And you don't need actually we were calculating for 1 year for your production needs, you actually need about 0.5 meter cube space, and you can we will make it larger granules, so it's safe for handling, but good for reaction.
What's going to be 7 cents per kilowatt hour? What's
7 cents per kilowatt hour for your energy storage from this aluminum.
that's that's almost impossible because that's going to be the electricity cost.
Yeah, I know.
So
That's what we are targeting, making it very exact.
I mean,
Yeah.
I would be very skeptical if I hear this because that's
But operation, of
that's
course,
the
you
price
have
of
the
electricity
operational
in
cost.
Iceland. So
Yeah.
how you can deliver the energy? Because you have no losses and you pay.
But with the OPEX and taxes, I think it's gonna be
That's
fun.
maybe a little bit more price for electricity, but not a lot. And as we've heard this,
Well, I mean,
there's a lot of losses. So I would say that's very hard to achieve.
Yeah.
in Quebec, the industrial rate for electricity is on the order of 1.5 to 2 cents Canadian per kilowatt hour.
Yeah, so it's a bit complicated, but
Yeah.
that's the lowest in the world. It's slightly lower than Iceland.
Mhm.
And then I'm sure there's taxes in the system. So that's not always available. Right? So that's the issue. That's what we also price in Iceland. We would love to do more of these things, but it's not price. So it's not clear whether we will have any energy for it. It's a choice that's being made within government, society, and power companies at the moment. If you ask them today, especially the power company, they would say, no, we're not going to do it.
Yeah.
That's power.
Yes.
Yeah, I think that's the idea. If we, leave Iceland just for a moment, I think that the idea would be to put smelters where there is the willingness and the availability of cheap power,
Yes.
and then,
Yeah, so I'm not disputing any that this is a
Okay.
great idea. Number 7 is still
yeah.
for somebody in the energy industry, this would be a
Yeah,
shock.
isn't it? Yeah. Okay.
Yeah, sort of hijack. I do have a question.
Okay.
Are the inert anodes, can you retrofit existing facilities? Or is it only going to be for new smelters going forward?
Yeah. This is like it's a bit of like also confidentiality.
Okay, so I'll just put another question.
But but you will need retrofitting because, as I said, this is like totally different technology. For instance, like we will, I think the size reduction from the conventional smelters, I think will be up to maybe even more than 60% the size reduction. You will need like much smaller aluminum smelters, for instance. In Hafnarfjörður there, how large space taken when you're driving to the Keflavik airport, you see, you will not need it. So it's because a lot of the space is actually taken for the anode shops. Einar can put that one.
Yeah, I just want to go back to one of Kina's first slides, since we were talking about the access to cheap energy. You say that most of the available renewables is solar. So do you think it would be realistic to use solar power in such a plant where you produce these fuels, or does it have to be 24-hour operation like another smelters? Are you this far already into the practicalities of production?
With actually inert anode process, we are thinking about that because of the isolation you have. You can actually have a very flexible operation.
Okay.
So, for instance, when there is a more power need, you can actually reduce the production or even shut down. And when there is no need, then we can think, and probably we'll be able to also use more efficiently the renewables, like solar, which I introduced. That's the idea with the, I think anode technology kind of offers a lot of possibilities that before we didn't have, and it's definitely a very exciting project.
Can I comment? Or
Yeah.
I guess the general discussion has already started. So. Just like I said, general comment, maybe some in the spirit of cooperation, possibly. Just to mention, I missed the beginning of the meeting, but then I was listening through my ears. We have now or will start a new energy transition project that we are leading here in Iceland, Verkís. It's a European Horizon project, 16,000 euros, 2.5 million Icelandic kroner. And it's about, like I said, energy transition. It's about energy transition with e-fuels. And in this project, we will use biomethanol and ammonia on board ships in transatlantic and global transport. And there we will use a reformer and cracker to make hydrogen and on board the ships as a demonstration project. And then using the hydrogen into fuel cells and producing electricity with a secondary auxiliary engine. The idea in the end is to be able to replace the first engine, but I mean, this is a demonstration project and I think first of its kind in a sense. And the reason we're trying both options is because in the future you will be able to, it's like with the cars, you know, you won't select, it's not going to be the same scenario all world round. So it's going to be some places where you use ammonia and the other places methanol. At least these are the, this is the context that the major players in this world are aiming for. So I'm just thinking out loud, you know, regarding one of the three speakers, because in this project which we are leading we have 18 partners, and we have really, you know, high quality partners in this project. So we have Fram, for example, they're doing research on the cracker and reformer. We have a company called Amnispura. I don't know if you know these names in this field. They will clean the hydrogen up. And then we have a company called Ballard, which is quite famous also in fuel cells. So we have a lot of entities within this project that are really exciting entities as well. So I'm just thinking, you know, I'm the innovation manager at Verkís, so I'm just thinking out loud, being like, maybe, I don't know if there's any spots where we can work together or anything, any input and things, but just so you know about this, to start in January, 1st of January 2024. It's going to be a 5-year project, and it's a retrofit project, so it's a demonstration project, so it's really going to happen on sea. So just so you know about that, and you can contact me. My name is Kjartan Dúrvíksson. If you're interested, that you can find me on the website. So you know, keep that in mind also, because I think internal cooperation also here is something that can help us also later on. I'm not a biochemist, but Katrin here is going to be involved in this project. She is a biochemist, and we have also Anna. So you know, we're going to be developing some skill sets as well during this project. So yeah.
I think this is definitely great input, and I think these occasions like where we actually get to know each other, because for instance we were and we were not aware that, you know, we are like going to be looking maybe in similar topics, and this is a great opportunity for us to get to know and maybe strengthen our power together, and especially as I mentioned, this is very relevant to Iceland. If we're gonna do energy transition, this will have to be through e-fuels as well, and I think it's great that Verkís is concentrating on it.
Yeah, I can definitely reach out to you. And how both Anna and Katrin is ex-students of mine. Okay. No, half your team. But definitely just things we can do. Also, just advocating for this in Iceland.
Yeah.
Well, somehow G and Brim are thinking about these things too. And
we're also in contact with people.
We're getting out together.
Entities in Iceland that are interested also in travel business and others. And we aim to try to, because this will not be a demonstration project in Iceland, we have parts of Hafnir involved. And the idea was that it would be great if we would have Iceland involved as a demonstration hub as well, but it was not possible. Yeah. But we are definitely interested in finding opportunities and aim for Icelandic and transferring skills and knowledge between them. They're only part of the team. There are 20 people, being involved in this.
Yeah. And we don't only have aluminium smelters here in Iceland, but also silicon smelters, which are also great e-fuel. As Kina short and good. You found the silicon was a part of the one that
it's underperformed.
Yeah,
and it was a big surprise. Okay. So big a surprise that I went and got the finest, the smallest particle size I could find, and held it under supercritical conditions for over 2 hours.
Okay.
And still was only getting about 25%
okay.
of the expected yield.
Yeah.
It was very, very surprising.
Yeah, it is surprising, yeah.
Yeah.
Because I know,
It should
yeah,
react.
yeah, it should, it should.
It should. And I thought, oh, maybe it's old, right? Maybe it has degraded. So I ordered fresh, you
Yeah.
know, came
Uh-huh.
sealed under in an inert atmosphere.
Okay. Okay,
By it, you mean, was it silicon or was it ferrosilicon or
No, it's silicon.
silicon, pure silicon?
okay.
Yeah.
Mhm.
French. Time to quit. Dus we have consumed the time we got, so þarf ykkur að ljúka þessu.
You just.
You should say, I should just say blessed, thank you.